Okay. Hello, everyone. Thanks for tuning into this talk. And I'm very excited to tell you about this work on random restrictions of high-dimensional distributions and uniformity testing with subcube conditioning. This is joint work with Clément Canon, Shi Chen, Gautam Kamath, and Amit Levy. And I'll also be mentioning some results that are joint with Rajesh Jairam. Okay, so let's get started. And I'll set up the algorithmic problem, which is the classic problem of testing uniformity. So the setup is as follows. We're given samples from an unknown distribution P, and I want to think about the case when P is supported on the n-dimensional Boolean hypercube, -1, 1 to the n, and we want our player Alice to design a randomized algorithm which can distinguish between the following two cases with probability at least 2/3. So in some sense, the first case, we have P is the uniform distribution over the n-dimensional Boolean hypercube, where each string appears with equal probability, or the case that P is epsilon far from uniform, and this will mean that the variation distance between P and the uniform distribution is at least epsilon. And the game here is to understand how many samples does Alice need. This is like a very well-studied problem, and throughout many years of works in property testing, we understand the complexity of this problem exactly, that this is 2 to the n/2 divided by epsilon squared. And generally, the task of testing uniformity of a distribution has complexity which is square root of the support size divided by epsilon squared, which in this case, if we think of the dimension of the underlying distribution as the growing parameter, is exponential in the dimension. In general, we want to sort of try to get around these exponential lower bounds, in particular if we're interested in high-dimensional distribution testing. And what this basically means is that we're going to need a new approach to study this problem. And there are really two options here. We can either consider restricted inputs, or we can consider allowing Alice a stronger access to the particular oracle. And sort of both of these options have been studied in the past. In particular, for studying restricted inputs, there's been work on testing properties of monotone distributions or testing Bayes nets with some low degree, or certain kinds of Markov random fields, as well as histograms. These are all ways that we can get around these exponential lower bounds by restricting the class of distributions that Alice needs to succeed against. On the other hand, there's this other work trying to prove polynomial upper bounds on worst case distributions. However, they're allowing Alice to access the distribution, not just via independent samples, but perhaps through a more stronger access. So here there's been work on what's called the conditional sampling oracle, or probability revealing samples, making queries to the PDF, as well as subcube conditional sampling. And in this talk, we'll really talk about subcube conditioning. This is simply one way in which Alice can access the distribution, which is more than simply independent samples. So the subcube conditional query was introduced in this paper by Bhattacharya and Chakrabarty in 2018, and the setup is as follows. Particularly, we have a distribution P supported on -1, 1 to the n, and now a query, a subcube conditioning query, is given by the string rho, which has its length n, and each index is set to either -1, 1, or star. Intuitively, rho will specify a subcube of the n-dimensional hypercube along the variables where rho is set to star, and the variables where rho is not set to star is set according to what rho specifies them to. So intuitively, Alice submits a query rho, which is the string, and that string specifies a subcube of the domain. And now what the oracle does, the oracle returns a sample from the distribution, it returns x sampled from P, conditioned on the event that x lies in the subcube specified by rho. So what this means is that for every index I, which is outside the set of stars of rho, the sample xi is equal to rho I. So the oracle returns a sample conditioning on this event. Just some background on prior work. The subcube conditional sampling model really comes out of the general conditional sampling model, which was introduced by Chakrabarty, Fisher, Goldhirsch, Matzlia, as well as by Canon, Ron, and Cervedio, where they're really studying testing distribution tasks, where the player can condition on an arbitrary subset of the support. So one can think of subcube conditional sampling as the particular case when this conditioning has to respect the underlying product structure of the domain. I mentioned that Bhattacharya and Chakrabarty, they showed several polynomial query upper bounds for some natural testing tasks, and in particular, they get around these exponential lower bounds, giving an algorithm for testing uniformity of complexity n squared over epsilon squared. The main result of this work is actually pinning down the complexity of testing uniformity with subcube conditioning to root n over epsilon squared up to polylog factors. I'd like to mention this work by Kanondijk, Nicholas, Kane, and Stewart. This paper where they study testing Bayes nets. This is a paper where they consider restricted inputs, and in particular, the most heavily restricted input that they consider is that of testing product distributions on -1, 1 to the n. So the problem here is that Alice receives samples to a product distribution, and she needs to determine whether the product distribution is uniform or not. And this paper, which I'll call CDKS, shows that the complexity is root n over epsilon squared many samples. The reason why I bring this up is that the corresponding lower bound on the sample complexity for testing a product distribution immediately implies a lower bound for subcube conditioning for general distributions. And the high-level idea is that product distributions are somewhat preserved under subcube conditioning. And formally, what I mean is that if Alice needs to make a subcube conditioning query to a product distribution, the oracle can simulate that by simply an independent sample. And the reason is that subcube conditioning tells the oracle to sample conditioned on a particular variable being set to some value. But if we are considering doing this on product distributions, then conditioning on a particular variable being set to some value or not has no bearing as to whether some other variable is going to be set. It's not going to change the distribution of the other variable because we assume that the distribution is independent across the variables. So in some sense, this implies that the lower bound for testing whether a product distribution is uniform gives a corresponding lower bound for testing a general distribution under this more powerful subcube conditioning queries. So the main result of this work is really understanding the upper bound, sort of the lower bound we get from this prior work. So what I really want to do is go back to this sort of picture of these two different options on how to study high-dimensional distribution testing. And for the rest of the talk, what I'm going to do is I'm going to focus first on what happens when we test for uniformity on the most restricted kind of inputs, that of the product distributions over -1, 1, because these will immediately give lower bounds for the corresponding subcube conditioning problem. The idea being is that we'll take the intuitions and the ideas that we get from the product distribution world and try to port them over to say something about general distributions when we allow the stronger subcube conditional query access. At a high level, the meta result that I want you to take away from this work is that general distributions can behave like product distributions after taking a random restriction. And I'll go into more specifics about what exactly I mean. I only mean that general distributions behave in a very specific way to product distributions, but I'll mention that this is very much still an open line of work, and I'll mention a lot of open problems in trying to solidify this connection between sample complexity of product distributions and the subcube conditioning complexity of general distributions. Okay, so that being said, let's first talk about what happens for product distributions. And the main reason why all product distributions are nice is because we have this definition of the mean vector, which pretty much captures everything we need to know about a product distribution. So the definition is the following. So if P is a product distribution supported on -1, 1, then I'll call mu P the mean vector. This is a vector on -1, 1 to the n, where each sort of coordinate of the mean vector is given by the expectation of xi, where x is sampled according to the distribution. In some sense, mu P simply cares about the marginal distribution and puts the expectation of the value -1, 1. And it's not hard to see that every product distribution not only has a corresponding mean vector, but that this mean vector is unique. In some sense, this mapping is really one-to-one. If you have an arbitrary mean vector, then there exists a unique product distribution whose mean vector is that vector. In particular, the uniform distribution, which assigns with half probability each bit is set to 1 and each bit is set to -1, has a mean vector given by the all zeros vector. And this work by Canondyke, Nicholas, Kane, and Stewart in 2017, the reason why they can come up with algorithms for testing, say, uniformity of product distributions is this intimate relationship between the total variation distance between a product distribution and the uniform distribution and the Euclidean norm of the mean vector mu p. So what they prove is that the variation distance between p and the uniform distribution is roughly the Euclidean norm of the mean vector. So the picture really is as follows. We have on the left-hand side the space of all possible product distributions, where I'm encoding each distribution as a vector in a 2 to the n dimensional space, where each coordinate of these 2 to the n points corresponds to the probability that some point on the hypercube is sampled. So here I have this middle point corresponding to the uniform distribution. This corresponds to the vector, which is set to 1 over 2 to the n for all 2 to the n indices. And on the right-hand side here, I have the space -1, 1 to the n, where I'm writing the mean vector of each particular product distribution. So what the theorem of CDKS shows is that if we take any distribution out here, any distribution whose distance in total variation, or the L1 distance to the uniform distribution is at least epsilon, or it lies outside this L1 ball, then the corresponding mean vector lies outside the L2 ball of the mean vector of the uniform distribution, which in particular is 0. So in particular, distributions which are far from uniform have mean vectors which have large L2 norm. And given this geometric intuition, there's some very natural tests that one may design. So for example, a natural test is to take a bunch of samples from the distribution and compute the empirical mean of these samples, with the idea that the empirical mean will converge to something close to the true mean vector. And then the Euclidean norm of the empirical mean should distinguish between the case that the mean vector is large, or that the distribution is epsilon far from uniform, or that the mean vector is small, and say that it is uniform. Okay, so this is one such test that you can design. So the natural question here is, to what extent can we port the same image, these same results about product distributions onto general distributions? So what can we say of the mean vector of a general distribution if we know that it's epsilon far from the uniform distribution? And perhaps it's not too hard to see that this sort of picture is totally doomed. The reason, there's a very simple distribution, P, which sets values to all 1s with probability 1/2, and sets values all -1 with probability 1/2. And the idea is that this distribution is clearly very far from uniform. In fact, it's only supported on 2 points in the hypercube. However, if we look at any of the marginals are completely balanced, and therefore the mean vector will be the all zeros vector. So in this case, there's one distribution which lies outside this L1 ball. However, the mean vector is exactly the all zeros vector. And the main point of this work is to show that even though this picture is not true, after we allow taking random restrictions, we can say something about the Euclidean norm of the mean vector and in relation to the variation distance to the uniform distribution. Before I tell you the main theorem, let me tell you about what it means to take a random restriction of a distribution. And the definition is very intuitive. We have a distribution P supported on -1, 1 to the n. Now we're going to set a parameter sigma, and sigma is going to correspond to the probability that some particular variable is set to a star. And then R sigma P is a distribution over random restrictions, which is given by sampling a random restriction row, where the stars, we sample the stars first, according to including each index I in the set of stars with probability sigma, and then we sample a fixed sample x from the distribution itself to sample the values of the non-stars, and then the restriction rho I is set to star if I was sampled included in the set S, and otherwise is set to the fixed sample from the distribution P if I is not included in this fixed set. So this is a way to sample a random restriction for a distribution. And what the main theorem says is that to some extent, this picture is true after we allow random restrictions. So in some sense, if P is any distribution over minus 1, 1 to the n, setting sigma to 1/2 for the probability of including some index as a star, then we have that the Euclidean norm of the mean vectors after taking a random restriction, where we vary the sampling probability according to all possible levels of sampling between 1/2 and 1/n, this is lower bounded by the distance in total variation up to polylog factors. Okay? And I claim that with this theorem, there's a very straightforward algorithm. So just to repeat the theorem here. And the algorithm for testing uniformity of general distributions with subcube conditioning works as follows. Well, we'll simply try all values of j, so that if indeed p was epsilon far from the uniform distribution, or this particular value is epsilon, then we're going to find some parameter j where the expected Euclidean norm is at least epsilon over some polylog factors. And notice that if p was indeed the uniform distribution, then any restriction will be uniform. And now the point is that after an averaging argument, we'll sample this particular row, and we can run the algorithm of the product testing case. In some sense, we have the property of a lower bound on the Euclidean norm of the mean vector, which will then allow us to distinguish from samples conditioned on lying in this particular restriction. And that's pretty much the algorithm, up to some caveats. So I want to conclude with some next steps and open problems. And all the open problems that I mentioned here will be that of solidifying this connection between general distributions and product distributions. So what can we say about the mean vectors of general distributions after random restriction? So perhaps the most natural question is to understand what happens for two unknown distributions, or what's the complexity of testing equivalence between two unknown distributions. And here, already Bhattacharya and Chakrabarty showed that these have complexity at most, n to the 5th divided by epsilon to the 5th. And let me just mention the other relevant result is what is the complexity of testing these two in the product distribution world. And here, Cannon, Dijk, Nicholas, Kane, and Stewart show that this complexity is the maximum of root n over epsilon squared and n to the 3/4 over epsilon. So perhaps my optimistic guess of this problem is that actually the complexity of testing equivalence with subcube conditional queries should be the same as what happens in the product distribution world. And in some sense, ideally, one would get that sort of the product distributions are indeed the hard cases. Another open problem is to think about this subcube conditioning query access as a membership query analog for learning distributions. And these are the results that I mentioned that are joined with Rajesh Jairam, where we did this to use it to learn K-Junta distributions from subcube conditioning. And we have some new algorithms using these connections between the random restrictions and the mean vector in order to learn K-Junta distributions optimally. Okay, another question is testing and learning monotone distributions. And here my optimistic guess is that what happens in the product distribution world should also happen for general distributions. And here's just some conjecture that saying that if you take a random restriction, then you look at the variables which are negatively biased, in some sense the values of the mean vector which are negative, and that these have Euclidean norm, which is given by the distance of the distribution to monotonicity. So this would be some structural result, which would then lead to an algorithm by simply taking a random restriction at each of these possible sampling levels. And let me just mention that there really is a natural pattern for some very interesting questions, is to consider a problem in the world of product distributions and to define, sort of see what structural results you can prove about general distributions while allowing taking random restrictions. So I think all these results are very surprising, and yeah, I think this is a great direction. But that's all I wanted to say, and thank you very much.